All right, so we are in the Sage landscape. So hopefully you can see some of the functions that we built up earlier. And now we're going to make use of them in at least this bitwise version of the CRYSTALS-Kyber public key crypto system. So as before, we have our random int binomial function. So that's going to be how we're going to generate some of those things. We're going to build up some of these nice little matrices using this little matrix poly representation. We're going to have our compress and decompress both at the number version as well as the vector version of it. So I think in the last video or a couple videos ago, we ran through that line to make sure that that all worked. I still have a typo in comprise in that one. I fixed the one, did not fix the other, but it'll be fixed now. Okay, so down below, again, the reminder on how we're going to build up this little A. So if we're going to feed in some list, so 1337, if I run it through this function, that will generate this list of lists that are going to look like this. And if I want to convert it into a matrix, I can just feed it into the matrix functionality like that. I specifically did not have it generate or return back a matrix because I want to use some list concatenation to build up the big A. So again, my big A is going to have like 4 of those little ones all struck together. So I wanted to at least be able to like take list plus list and then just like glue them together. Down below is going to be a bunch of our public parameters. So here I used, my n to be a 4. I took q to be my 3329. Here I took my new, technically it should be an eta, but I don't like having to spell that out. So I just wrote out new then for my little random number bound thing. So I wrote it up as a u. I think maybe in one of the other submissions it was written as a u, or in some other file it was a u, but whatever. So it's u or an eta, however you want to write it. That's going to be how we're going to generate some of those random numbers with that specific spread. So what that's going to say is that I'm going to have random numbers that are going to go from like -2 up to +2. Most of them are going to be swelled around the 0. My du is going to then be a 10. Here I took dv to be a 3. I could take it to be a 4. I could take it to be whatever I want to. We're just doing toy numbers right now. I did use the actual real q, so the 3329, just to kind of showcase where that emerged from. So the 3329, if I subtract 1 from it, it's 3328. So that's divisible by 256, which is 2 to the 8th. And then that's multiplied by that extra little prime 13. If you wanted to see what other primes could be replaced for that 13, if you just blast through some of them, if you were to take that to be a 3, so if you had 256 times 3, and then add 1 to it, that gives you that other 769. So you could run that as the q, though that's not as great. I think there was a little comment that I had in the notes from the original NIST submission about why that one's not necessarily ideal. So they wanted to go one step further. And if you go down this list, you can see that the next one that actually worked was at this level. If you wanted to, you could keep on marching and you could run it up to like here if you wanted to have that same structure as well. So we're living in this one, though you could choose that q to be some cute prime as well. So I think if you ran it on like 7331, everything would totally run through as well. So if I run that, that's at least all turned on. So my key gen, so here I'm going to just, feed in those same 4 toy polynomials. Obviously, those numbers range nowhere close to the upper bound of q minus 1 that they could. So I think that what I could run it was like q being 17 or something, because then all of those numbers at least less than 17. So I'm going to feed in those as lists. I'm going to then store each of those as this fancy kind of list of lists where the rotational structure emerges. And then right now, these are not actually stored as a matrix. They're again stored as lists of lists. So I can easily build up my A by taking, first row of this thing, adding it to the first row of that thing to give me my first overall row of A. And that's what's happening down here, is that I'm going to go through, from 0 to 4 or 0 to 3, so 4 entries. I'm going to take and build my first 4 rows of my big matrix. So here you can see the top left corner is then going to be the twisted version. There, top 4 is going to be the twisted version of 1337 with the negatives, and the other one's going to be the 42, 143, and then the twisted version of that. So move the 3 over, move the 14 over, move the 2, but then as they move over, they come up as negatives. Same thing for the bottoms. So you end up with this big old matrix A. So it's 2n by 2n or 8 by 8 here. And then we're actually going to turn it on. So in the next part, we're going to then start building up our little vectors as random ones. So the SA and the EA. So here, because my new or my eta was chosen to be a 2, I'm randomly generating numbers from -2 to 2, though most of them are going to be between -1 and 1. So a couple of them might flex out to be a 2. So here I have those ones. I'm not going to rerun this just because I know that it all works down below fine, but I'll rerun it later on. But just in case something funky happens as I turn things back on and turn things back off, I don't want to have something predefined and something else not predefined. So I have those. They are what they are. In the next step, we can obviously build up our public key. So we're going to take A, we're going to multiply it by that little s, so the twisty fancy multiplication. I want to reduce everything modulo q, so I'm going to use this vector with the GFQ and the matrix with the GFQ as well. So if I didn't have those, it would generate the same PK, but my final answers would not be reduced modulo q. So you could later do that, or you can bake it into that little definition as well. And then I'm going to add on my little error term. So my little smudge factor, that little EA is going to be stuffed at the end. Okay, so that's PK. It is whatever it is. The hope is that if you have this, it's really hard to figure out what the S and the E were that made it. It's probably not so hard when there's only 8 terms in it, but it still hopefully should be challenging enough to figure out what those are. So here, these obviously have, range of 5 different things. So there's what, 5 to the 8th or something. So 390,000 possible S's and 390,000 possible E's. So if you start cycling through all possibilities, you start to get a lot. And if those flex out to be, 500 entries long, things start to get obviously significantly worse. Okay, so that's it on the encryption side of things, or on the keygen side of things. So encryption is going to look very, very similar. So we're going to have the same SB and the EB, so generated in the same way that Alice generated hers. We're going to construct this little PB, so this PB for Bob, in that we're going to take this SB, so his SB multiplied by the transpose of A. So we're going to feed in the transpose command, and then again, add on that little smudge factor EB afterwards. That PB becomes this thing. That is not made publicly available. So right now, kind of keep those numbers in your mind. We'll scroll up to it in a little bit, in that we're going to compress some things and we're going to decompress some things. And later on, we'll see this PB-ish emerge up to a little bit of error. So when Bob actually then encrypts his message, what he's going to do is he's going to take his favorite bit, so either a 0 or a 1. Again, if you wanted to add in additional bits and other things, there's some XORing and some other later, pre-processing that needs to emerge. But for right now, at least for kind of the fun math, 0s and 1s work totally fine as well. So to do that, he's going to take his nice little SB and he's going to dot it with his little PB. So we're going to see those things emerge in the world. And actually, that's probably a typo. That's not supposed to be a PB. It's supposed to be a PK. All right, let's regenerate those things. Well, let's just regenerate all of them for now, because I might have had a typo in it. Regenerate that. Regenerate that. Okay. So we're going to have those, and that part is supposed to be the PB. Okay. So when he does his definition of VB, it's going to be SB. So his private little SB dotted against Alice's public PK, which is happening there. And then we're going to add on the decompressed version of M with 1. So that is then set up like that. Cool. All right, so then on the second process of this, what we're going to do is we're going to compress his PB. So again, we're not revealing PB to the wild. We're going to reveal a compressed version of PB. So again, PB is this thing right here. It's changed now that I regenerated some of my numbers. So 37, 8, 6, so on and so forth. We're going to compress that thing against the DU, which I think we took to be like a 10. And then likewise, we're going to compress this VB. So it's currently 1669. And we're going to compress that against, I think, the DV we chose to be a 3 in this one. So we're going to re-execute that, and we'll see that. So again, make sure that's all set. So we're going to have this as then our publicly available C1 and C2. So that's going to be what's then sent out into the wild. Again, C1 is a vector. Those numbers, obviously there's 8 of them. So those numbers are emerging from this compressed vector function. So that just compressed each of those entries on their own. So I took each of those and I compressed those. And then my C2, again, was compressing the VB against the 3 or whatever DV happened to be. So on the decryption side, Alice is going to first try to decompress this C1, and then we're going to try to decompress this C2. So the hope, if you kind of go back and look at the C1 was generated by compressing PB. So when I decompress it, the hope is that it's kind of close to PB. And let's see if I can copy PB just to kind of see how close that might actually be. So PB was actually this. So 37, 8, 6, 3, 3, 2, 1, 29, 14, 8, and 3, 3, 0, 0. So you can see that the decompressed version of it's not exact. We got a couple little onesies that we're off by. So 36 to 37, 7 to 8, 7 to 6, 3, 3, 2, 2 to 3, 3, 2, 1. 29 matches perfectly with 29. The 14 and 13, 8 and 7, and the last one matches perfectly as well. So you can see that it's a little bit off on how some of that stuff all panned out. The same thing is going to occur on the other side. So C2 was a compressed version of VB. So VB was 1669. And if you look down here, the decompressed version came back to 1665. Again, it's not perfect there, and it's not intended to be, is that we're going to have little errors that are going to emerge, but they are pretty close. And again, that makes this process even worse. So publicly, that PB is made not publicly available. Anybody that wanted to could run the decompression, and they could say, okay, Bob's PB looks like this, but it's not exactly what Bob's PB was. So not only are you trying to figure out his S and try to figure out his E, you're also not given perfect information about what his actual sample ends up being, because it's within a couple little wiggle rooms as well. So it's layers upon layers of like little onesies and twosies that all start adding up pretty dramatically once you start having thousands of these little operations that have to emerge. So it's not perfect, but it doesn't have to be perfect. So the hope then is that if we then run this final compression process, so what we're going to do is we're going to take this little VA, so the thing that's generated right here, so this number, and we're going to subtract off the UA, so the thing that's kind of pretending to be Bob's PB, and then dot that against our private SA. So that little number, when I compress it and do some rounding, which obviously happens in the compression, that it should either round to a 0 or it should round into a 1. And if I run it there, it does in fact kick up the 1, which is what my message was. If I rerun this with a 0 and cross my fingers that everything is set up, so if it's a 0, then my VB turns into a 4. My C1 is going to be the exact same because that obviously didn't change at all. And then if I come down into this process, and then if I run this last little bit, it'll then end up generating a 0 as well. So it does work. It's kind of cute. Again, it's single bits. So if you run through some of them, obviously the numbers are toys, so a lot of stuff zeroes out probably too much, where you're like, oh, my VA was still a 0, and obviously that's going to round into being a 0 or something like that. That, again, is sometimes an issue of the toy number stuff. So if I wanted to go back up here and then move away from just these, so if I actually have my randomly generated things, I can totally do that as well. So I can make my A just a little bit bigger and then rerun everything from here on out, which should hopefully be still set. So again, Bob's PB starts with 1791 and 2309. So when I compress it and then get rid of that because that's not actually accurate anymore, and then decompress it, you can see they're pretty close, not perfect, but again, it does decrypt into this little 1. And if I go back and turn this into a 0, I can do that and see 0 emerge as well. So it's cute, it's fun, it's tidy. If I wanted to flex it up to something bigger, I have another slide there, another page. Let me double check to make sure Bob's stuff is actually done correctly, as I had a typo in the last one, and I probably have the same typo in here. So VB was taken to be, this has got to be the PK. And this is the PB. Okay, so if I run this stuff and turn it all back on, what's happening here is that I'm going to run it with the actual honest to goodness parameters. So 256, here I'm going to run it with like new being a 1, which is actually the same thing as like the notes version of it being a 2. If you look really closely, their sum starts at 1, whereas in the code it will start at a 0. So it'll flex out correctly from there. So here I'll take it to be 10 and a 3. So it probably should be like a 10 and a 4. That I really don't care. And then I can randomly generate some things. So these are going to be pretty big. So I'm not printing out what these things happen to be. Later on, I'll print some stuff, but the actual matrix A is about 500 by 500. So if I randomly generate my S's, make my public key, so PK, you can see that it is 500 numbers long. Each of those numbers obviously modulo Q, so it's a beast on its own. Encryption is going to work the same way. We're going to generate this PB. So it's got a whole bunch of numbers. That's not made publicly available. So what we're going to do then is we're going to take our message of M. We're going to compress some stuff. And then when it comes to the decryption, we're going to decompress some stuff. And then we're going to hope that the message is in fact a 0 or is a 1. I think this one was the 1. And if I go back and try to change it into a 0, I can do that as well. And it sees a 0. So yay, it all works. It's most exciting. It's like the most exciting version of seeing a 1 or a 0 emerge that you would ever want to. Just because we got only probably like, not 5 seconds, but just a couple minutes. I'm just going to jump back to the notes because I don't feel like making it as a complete separate own little video. So I'm just going to showcase this because I didn't give it the full like formal treatment anyways. So just to kind of, let me pull my screen actually to see what you should see. So the very last page of the notes, I do have just kind of some rough handwork process on kind of why you would expect some of this stuff to actually emerge and kind of work. And it comes into play when you start the decryption process. When you look at this VA minus UA dotted with SA, the very first thing is like this very much so squiggly equals, because I'm just loosely saying that this UA is going to like regenerate what it should be, and that the UA is going to be Bob's PB, and that the VA should be the VB. And if those were actually exact, then you can start this process of back substitution and seeing all of these things emerge like we would expect to. So that's what's being flexed out there. You can kind of poke around it if you'd like. It looks very similar to what we saw in section 9.1, where we played around with that toy system that didn't have any compression or decompression, in that we had a whole bunch of these dot things all that disappeared. And then voila, we were left with something that was kind of small. And then when we multiplied it by something, well, then it rounded to 1 or to 0. So it functions almost identically to what we saw then, except for that first step where we're, very, hand wavily saying these are close enough to that. I didn't include any of the like formal like error bounds and stuff like that. Again, we're kind of running low on time for the end of the semester, and I wanted to talk about some of the error correcting codes. So I'm just going to kind of punt it to the actual submission. They have a couple pages for kind of the validation as to why it works. Otherwise, over winter break, if you want to chat a little bit more about kind of the formalities of like why all of these bounds are so and things like that, we can totally chat as well. But for now, I'll probably pause it to there and just kind of let you play around with it and see some of these little bits, see how they all emerge, play with them in some of the activities, have a good time, draw a whole bunch of lightsabers, better lightsabers than mine. Correct me on all of my incorrect lightsaber knowledge that I'm most certainly lying to you on, but you can send me a lightsaber too, and I can add it to my office. I don't think I have any Star Wars-y stuff in my office. I have a whole bunch of, Optimus Primes and things like that for obvious reasons, but no Star Wars stuff at all. So maybe I can get some Star Wars swag in here and go from there. So anyway, I'll pause it there. I'll let you play on some activities. So as I mentioned, I took these last couple sections and I'll probably combine them into one activity just so you can kind of do some of the hand multiplication, play around with this system to see it all in its glory, to morph it and modify it and see it all shine. And then we'll jump into some error correcting codes and see at least the runner-up or another version of some post-quantum crypto stuff that does not make use of lattices, but makes use of error correcting codes. We'll go from there. So adios, have fun.